Now I will go to the third lecture of week 5 of this course, and in this lecture we will look at point groups in more detail. Okay. We have already seen about point symmetry operations, space symmetry operations, and we have also said where the concept of a group comes from. Okay. And now we look at point group, which basically represents the set of all point symmetry operations in a crystal. So, in this lecture we will talk about point groups. Now, we have already seen the crystal system classification based on symmetry, and we had various essential symmetry requirements for the 7 crystal systems. Okay. Now, so this gives us 7 crystal systems. Okay. And further, if you look at the lattices, okay, if you look at the various lattices that are possible in each of these systems, they are classified into 14 Bravais lattices. Okay. So we can get those by looking at the unit cell for each of the crystal system and having it either centered or primitive. So that gives us 14 Bravais lattices. Now, what we will see today is that this leads to 32 crystal classes or point groups. Or point groups. I will not show all the 32 point groups, okay, but I will just mention that that if you look at the these crystal classes or point groups, okay, so these are based on symmetries, and in particular point symmetries of the unit cell. Symmetry of one primitive cell. Okay. Now, let's we'll see some of these 32 crystal classes in this lecture, and then we will see in the next lecture how these 32 crystal classes or point groups are expanded to many more space groups. So, let's look at point symmetry operations in a crystal, and let me take the example of an FCC lattice with a single atom basis. Okay. And let me emphasize that we are just considering one unit cell. Okay. We are just considering a single unit cell, okay, which is cubic in shape. Okay. So, for an FCC, if you just take one cell, okay, you have it is cubic in shape. And we are just looking what are the symmetry operations that will take this cube, okay, this cube with atoms at the corners and atoms at the face centers. What are the symmetry operations that will leave this cube unchanged? Okay, so we will show the face center atoms. Okay, so these are the 6 face center atoms and the corner atoms. Okay, now the question is, you just take this single unit cell. Okay, so we are considering only one unit cell, and we are asking what are the symmetry operations of this unit cell. Okay, what are the operations that will leave this unit cell unchanged? Okay, now we can we can start with the threefold rotations. So clearly there are 4 threefold rotations. Okay, let me use a slightly different color to write this. So I'll just say 3 threefold rotations. Okay, and I'll just show one of those. I'll show here. So one of those is this one that is passing through the body diagonal, and you have 4 of these. Okay, so you have 4 threefold rotations. This is a 3. Clearly there are 4 of these. I am not going to show all the 4. Okay, but what else is there? Now you can have 3 fourfold rotations. So okay, and the 3 fourfold rotations will, I'll just show one of them that comes out. This way. So this is clearly a fourfold rotation. Okay. What else can you have? Well, it turns out that there are other rotations that are possible. Okay, there are 6 twofold rotations. Okay, and these rotation axes actually go from, so write 6 and this goes from the center of one edge to the center of the opposite edge. So that is a twofold rotation, twofold axis of rotation, and you can easily see that you rotate about 180 degrees above this, you will get an equivalent configuration. Okay, there are 6 of these. I am not showing all the 6, I am just showing one of each of them. Okay. Now other operations in addition to this, and yes, indeed there are a lot of other operations. Okay, and again I am not going to show all of them explicitly, but let me mention a few. Let me mention them. So there is a inversion. Inversion about this origin, about the center. Then there are mirror planes. So there are 9 mirror planes. Okay, and you can easily see these 9. Okay, if you just take you can see these quite easily. Okay, so you'll have diagonal mirror planes, and you'll have along this midpoint. Okay, so they will all be mirror planes. There will be total 9 of them. Okay, just to show some of these mirror planes, let me I'll just show one mirror plane that is perpendicular to the screen. Okay, and it passes okay. So you will have I mean, this is, I don't know if this is a mirror plane. Okay, it is actually perpendicular to the screen, and it goes through the I mean, it cuts the cube directly into 2 halves. Okay, so this is okay. So that's and there'll be 2 others. There'll be 2 others, and there'll be 2 diagonals in each on each of the directions. Okay, so there are a total of 9 mirror planes. And so now you can take each of these and then there is the identity operation. I'll just call it identity. Okay, this is just one identity. Okay, so now if you ask how many configurations you get of the how many different configuration or how many different configurations do you generate from all these operations. So if you have a threefold rotation, okay, then the threefold rotation corresponds to rotation by 120 degrees. So you can have rotation by 120 degrees and rotation by 240 degrees. Now threefold means you rotate it, you do it 3 times, you get back the identity. So you get two distinct two new configurations for the due to this due to each threefold rotation. So you can see that if you have 4 threefold rotations, you will generate 8 new configurations. Okay. If you have 3 fourfold rotations, you will generate 9 new configurations. Okay. So essentially the number of distinct symmetry operations are 8, 9. Here you will have 6 distinct, because here you will have 1 distinct, here you will have 9 distinct, and here you just have the original one. Okay. So this is the total order of the symmetry operations, or the number of distinct symmetry operations that you have. Okay. In addition to this, you have some more operations. So for example, each of these twofold, so in addition to this you have some roto inversions. Okay. You have 4 bar roto inversion. Now this 4 bar roto inversion axis. Okay. So actually the 6 twofold rotations, okay, each of them corresponds to a 4 bar roto inversion axis. Okay. And similarly there is a 3 bar roto inversion axis. Okay. Actually you will get from the 4 threefold rotations. Okay, you will get 8 roto inversions. Okay. Now this 8 actually should be 6 bar roto inversions. Okay. So this each threefold rotation, okay, corresponds to a roto inversion axis. Okay, by half that amount. Okay. So this generates an additional 6 operations, and this generates an additional 8 operations. So the total number of operations, if you add this, add all of these, okay, the total number of operations, okay, will come out to 48. So the order of the point group is 48. Okay. And this point group is given the notation in point group terminology. This is called as OH, or octahedral point group. This is a terminology that is borrowed from molecules. Okay. We'll come to the description in Hermann-Mauguin convention, okay, a little later. I mean, this is called M3M in the Hermann-Mauguin notation. Okay, we'll explain this in more detail in the next lecture. Okay, but the point is that you have 48 different symmetry operations. Okay, they correspond to the octahedral group. Okay, now a few things to be kept in mind. Okay, you should keep in mind that that you know, this 4 bar roto inversion, okay, if you apply it twice, you will get a C2, you will get a twofold rotation. So, 4 bar roto inversion corresponds to rotation by 90 degrees and inversion. So, if you do it 2 times, you will get rotation by 180 degrees and 2 inversions will cancel each other. So, that will just be a rotation by 180 degrees, which is just a twofold rotation. Okay. So, actually the number of distinct operations that are generated by this is only 1. Okay. And again this is just a property of this crystal. Okay. So, these are the distinct operations that are there in the crystal, and the point group of FCC is octahedral. Okay. Now, next we can ask the question, see now keep in mind that we just looked at one unit cell, and whatever operations we did, we never mapped it, all these atoms were mapped onto each other. So, the cube remained as it was. Okay. You never considered an operation where this atom was, where one atom from one unit cell was mapped to a neighboring unit cell, to an atom from a neighboring unit cell. Okay. Okay. Now, what about a BCC lattice with a single atom basis? Now, again you will consider only one unit cell, and you will consider a BCC unit cell. So, you have all the atoms at the corners of a cube. And one at the body center. Okay. Now, again you can see without too much difficulty that you still have the 3 axis of rotation. You have the 3 4-fold axis of rotations. You have the 6 2-fold axis of rotation. Okay. And this is the order of rotation. Okay. So, the order of the rotation axis. So, you have 3, you have the, this is the number of different axes. So, you have 3 axis, 3 4 axis, 6 2 axis, just like earlier. You have the inversion center. Okay, again just like in the previous case. Okay, and you still have the 9 mirrors, right? One inversion center. You have one identity. Okay, I will call it O1. Okay, which is always there. Identity is always there, and you can again convince yourself that you still have those. You still have the 6 4 bar and 8 6 bar. Okay, so, you still have all those. Okay. So, again you have 48 operations. Okay, and again the point group is octahedral. Okay. So, BCC and FCC and simple cubic also have same point group, or they belong to the same point group. Okay. So, the point group of BCC and FCC is the same. Okay. There is no difference between in the point groups of FCC and BCC. Okay. However, keep in mind that space groups are different. Okay. Space groups, we will show that they are quite different. Okay. In fact, you know, since we considered only one unit cell, okay, so we are just looking at one of these cubes. Okay. Now, essentially the whatever the symmetries are there in the cube, they will be there in BCC or FCC. Okay, changing it from BCC to FCC is not going to change the symmetries of a cube, right. So, it is expected that BCC and FCC, okay, will have the same point group, okay, and you can call it octahedral or M3M. I'll explain this M3M again. So, this is in the Hermann-Morget notation. Okay. But essentially there is only BCC and FCC belong to the same point group. What about diamond? Okay. Now, again, if you just consider one unit cell, and you take your additional points that we like to put that we always put for diamond along the body diagonals, along this one, 1/4 of the body diagonals along this one, and along this one. So, now again it should not take you too much convincing that this still has the 4 3 axis, it still has the 6 2 axis, it still has the 3 4 axis, and it will still have the. Now, diamond, if you just consider one unit cell, okay, then clearly diamond does not have a center of inversion. Okay. If you just look at a single unit cell, okay, then it would appear that diamond does not possess a center of inversion. Okay. However, we already saw earlier that there is an inversion center, okay, and that is located between the corner atom and the center of and one of the atoms on the body diagonal. Okay. So, there is an inversion center. Okay. Now here you have to, if you want to see this inversion center in a single cell, okay, then you have to take a slightly different cell. Okay. So, choose different cell. Okay. And it is not very hard to do that. Okay. So, you just take your cube, okay, and if you choose it in a slightly different direction, okay, so that this is this point that goes halfway here, okay, is now the center. Okay. So, if you choose a unit cell that is centered here, okay, then again you can easily construct a unit cell that is centered here, and again with just one cube, that is instead of centering the cube at 0 0 0, you center it at no, instead of centering it at half half half, you center it at 1 8 1 8 1 8, and you will see a cell where the inversion axis is in the inversion center is very clear. Okay. And similarly, when you do that, you will also see that all the remaining symmetry elements, okay, which are part of this, like you have the 9 mirrors, you have the 1 identity, you have the 6 4 bar, and you have the 8 6 bar. All these are there. So, you get 48, and this is also octahedral M3M. Okay. So, again this is something that you should work out. Okay, you should not take these as given to you. Okay, these are slightly involved to work out, but you can show that if you choose one unit cell, if you center your unit cell appropriately, then you will see all these symmetries of a diamond cubic lattice. Okay. Now, finally, let us take the example of a hexagonal closed packed cell. Okay. And now again we are going to consider only one cell. Okay. But again, as we had shown earlier, that it is possible to you can choose your cell so that it shows a center of inversion. So while usually we take the HCP in this form. Okay. Now, usually we often take our unit cell having an atom at the corner. Okay. So, if we take it in this form, and if you take it in this form, then only one of these will be in the middle of the cell, and it won't be exactly at the center, it will be slightly off the center. Okay. However, what we said is that it is possible to choose a slightly different shifted unit cell, okay, where the midpoint is located. The midpoint of the cell is located directly in the middle of this line right here. Okay. So if you choose a new cell where the midpoint is located here, okay, and I will just show it schematically. Okay. Now, if you choose such a cell, okay, so this has an inversion symmetry. Actually, yeah. So it has inversion symmetry with respect to these to the atoms that are there in the cell. Okay. And now you can look at the various symmetry elements. Okay. So the symmetry elements in an HCP crystal are the following. So there is one 6 axis, okay, and in fact this is a 6 bar axis. Okay, it's not a 6 axis, it's a 6 bar axis. Okay. There are 6 2 axis, there is one mirror. This is in the horizontal direction, and there are 6 mirrors in the vertical directions. Okay. And in addition there is an inversion center, and there is a one identity operation. Okay. And now, so the 6 bar axis will generate total of 5 symmetry operations, including. So, if you do 6 bar twice, you will get a C3. So, including that you get 5 symmetry operations. You will get so 6 bar includes C3. Okay, so 6 bar operated twice will give you includes a threefold rotation. So 6 corresponds to rotation by 60 degrees. So if you do 60 degrees and inversion, again you do 60 degrees and inversion. So totally you have done 120 degrees and you have cancelled the inversion. So that is a threefold axis of rotation. Okay. Then there are 2 axes of rotation. There is one operation due to a mirror. There are 6 other mirrors. There is 1 inversion and 1 more. Okay. And this falls in the group. This symmetry group is called D6H in molecular symmetry language. And in crystallographic symmetry it is called 6 by M. Now let's look at the 6 axis a little more closely. Okay, so let's look at 6 axis a little more closely. So you have 6 bar. 6 bar square is same as 3. Then you have 6 bar cube. Okay, 6 into 3 is nothing but the 2. Okay, so this is nothing but 2 bar. Okay, and and then you have 6 into 4 is just 3 square, and 6 into 5 is 6 bar into 5. Okay, so that will give you write it as 6 bar square. Okay, and then you have the identity. Okay, now 2 bar is actually nothing but a mirror. Okay, so so there will be some reduction in the number of symmetries. Okay, due to this 6 bar axis. Okay, so it won't actually be 5. Okay, so the number of distinct symmetry operations due to this 6-fold axis, okay, will be so this will be only 3 distinct operations. Okay, so you have total 18 operations, and D6H is a group of order 18. Okay, so with this I will conclude this discussion on point groups. Okay, and I encourage you to actually look at various crystals of different kinds of crystals. You could look at things like sodium chloride, you could look at zinc blend, you could look at various crystal structures and try to identify the point groups. Okay. Now, these point groups you can also find in the international tables of crystallography. Okay, there are several places where you can actually find the point groups and all the symmetry elements, but it helps to actually work out some of these point groups. Okay, and you will realize when you actually work them out, you will realize some of the subtleties that are there in the definition of the point group. Okay. So I will conclude this lecture here. In the next lecture, I will talk about space groups. Thank you.